Simon and Andrew, and for CS221 final project, we created Gatsby, which is a program that produces course schedule for students using genetic algorithm and Tabu search. So let's dive straight into it. The problem we want to solve is to create four-year plan for CS majors of any specialization track. In CS221 assignment, we implemented course scheduler using factor graphs. In this project, we want to scale it up and try using different approach for it. So for this types of problems, we could implement it using backtracking algorithm, but it takes exponential time complexity. There are heuristics such as AC3 that can improve the runtime, but the time complexity is still exponential. In this project, we're trying a new randomized algorithm called genetic algorithm, which usually runs in faster time and is dependent on the max number of variations, population, and length of chromosomes. I'll go over this algorithm step by step. So some keywords to note: chromosome means one possible set of assignments to all variables, and population is a set of chromosomes in current generation. Fitness is similar to factor and factor graphs that we studied in 221. Now, in selecting chromosomes, we choose chromosomes with probability proportional to its fitness, so that chromosome that has higher fitness level gets chosen more often for the future generations. For crossover, we produce offspring by interchanging data of parents, and mutating chromosomes is necessary to maintain diversity of the population for future generations. We modeled this problem using a set of hard and soft constraints, and the goal of the genetic algorithm is to produce the chromosome that satisfies all of the hard constraints and most of the soft constraints. The first step would be to initialize population. To do this, we produce chromosomes, each representing a possible four-year plan. Each cell in this chromosome would represent a course ID, and the value of that cell will be corresponding to what quarter each course is taken in. Next, we have to evaluate fitness of these chromosomes. The way we do this is we apply penalties based on hard constraints and soft constraints broken. Then we rank our chromosomes and select chromosomes with highest fitness to be passed on to the next generation. Then we apply our crossover function, then mutation function for diversity. So this is the genetic algorithm. Now I'd like to demonstrate how the baseline genetic algorithm works and pass on to Simon.
Right, so as you can see, this is the genetic algorithm running, and you can see that it runs pretty fast, but it converges to a suboptimal value pretty quickly. So the question is, can genetic algorithms be improved? The problem with genetic algorithms right now is that we are randomly sampling trivially suboptimal schedules. So we found that we could guide evolution to the global optimum by employing some kind of local heuristic with it. We can we can optimize for the number of generations with this way. So we decided to use Tabu search, which was first proposed in 1980. The essence of Tabu search is to explore the neighborhood of each chromosome and kind of move it in the direction of either the improving neighbor or the best non-improving neighbor within that neighborhood. So some terminology for Tabu search: the neighborhood is defined as a set of solutions that's generated by applying a minimal transformation. Our transformation is going to be a flip where we change the value at that index. Move would be the transition from the solution to the neighbor. So if we flip the third gene to -1, it'd be 3, -1. And Tabu list would be record that number of moves, and it discourages moves that revert back to its original state, so it prevents cycling. So Gatsby essentially does the genetic operations, genetic algorithm, but it applies Tabu search on each chromosome to get a better generation each time. So step by step for Tabu search, let's say we have this chromosome, we would flip each gene to another possible value and get a set of neighbors. We would evaluate those neighbors and return either the first improving neighbor, or if none exists, we would select the best non-improving neighbor in that neighborhood, and we would do the same search process, but this time with that neighbor, and we would record the most recent move in the Tabu list so that it doesn't move back to that. So that's Tabu search, and now I'm going to show you how that works in action. So you can see that with Tabu search, each generation does run a bit slower. However, you can see that it makes non-improving moves here, but each generation is more impactful in that it drives it up towards the maximal fitness, which in this case is 0. So it already converges, it already goes down to 4 digits by generation 14. So some of the results is that genetic algorithm converges at a suboptimal value within 120 generations, whereas Gatsby converges to the optimal value within 30. So that was our project where we used genetic algorithms with Tabu search to solve the Stanford CS course scheduling problem. Thank you very much.